So, as I was saying, it was kind of interesting to follow Dave Thomas as he speaks about legacy code, because that's the thing I typically do in the industry. But this is a different thing, okay? And it's kind of interesting that there are a lot of things that we just don't really question very much in software development. And I think we're starting to go and question some of them a bit more. For instance, at this conference, there were 2 sessions on error handling, okay, that were nice to see, because I felt like error handling has been one of those topics that, you know, we kind of know about, we kind of do it, but we don't really sit down and think about it systematically. And so a lot of this material just kind of started with that frame of like, you know, what can we do about error handling, right? And then kind of carry on things into like, how do we start to like remove conditionality in code and things along those lines. So that's what this title is about, Unconditional Code. The thing is, what I want to do is start to question a couple of things, okay? What can go wrong with this piece of code here? I'm not even telling you what language it's in. Can anything go wrong with this? Yeah, lots of things, right? Okay, and it's like, you know, we could probably start listing all the different things. We could have arithmetic overflow. We can have all sorts of crazy things happen. But in general, you know, when we write an expression like this, we have some kind of an intention. It's like we want this particular thing to work. And if we're unlucky, something bad happens. We throw an exception, and we segfault. We do something crazy. And we have to go and deal with the possibility of all these errors, right? So, yeah, it's kind of interesting that, you know, as I mentioned, some people have talked about error handling across this conference. And you know, particularly Joe Armstrong yesterday was going and talking about, you know, if you're on a single machine, you're in trouble because if anything goes wrong, you're in trouble, right? You don't really have much redundancy, and essentially he tries to go and get this model of going and having, you know, many processes, and so that when some go down, others can come up, and then you have a great degree of robustness in your system. But let's go and dig deeper into this. The thing that I really object to is logging. Actually, no, I don't object to logging. But the thing is, I felt for a long time in my career that I just don't really like logging, at least the way it's been traditionally done within the industry, right? And the thing that makes that kind of odd is because you can't make like a good cogent case against logging, because it's one of those things that everybody feels is necessary, and you know, going and looking through things post-mortem and understanding what's going on is really a very valuable thing to do. But it's funny because it makes the code look ugly, doesn't it? To have like scattered log statements all the way through it. It's like, you know, if we have this idea about single responsibilities, you know, it's kind of like, well, what's the responsibility of this piece of code? Oh, to do this, 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 and then also log what's going on with it. And that kind of mixing of responsibilities can kind of be kind of awkward. And it's interesting about this because I feel the same way pretty much about error handling, right? It's kind of like it breaks the mainline flow of the application. And because of that, it tends to obscure whatever logic we're going and trying to get across. But you will see error handling code scattered throughout most applications. And I think it's really through a lack of understanding and a lack of discipline we end up going and doing this sort of thing. So I want to go and kind of raise this question. What if noticeable error handling is a symptom of bad design? What can we do about this? And we're going to go through a series of things to kind of like explore that idea. Okay? And it's not just at the level of code, right? It's kind of like there are all sorts of things that, you know, I think errors in general are something we really ought to go and question. You know, here's like reviewing your order for Amazon, and here's a problem which occurred when you're going and trying to go and pay, right? It's like, at this point, the software has failed the user, right? So we basically have to go back, and we have to go and tell the user about this particular problem, and you know, go on and carry on. And we don't want these particular things to happen, right? And it seems with a bit more effort, we can actually go and move towards this space where, generally speaking, our code does run unconditionally. It just goes and does what it's supposed to do. If it can't do a particular thing that we want it to do, it can do something else good for us, and something else that we can notify the user about and say, hey, we've done this for you because, you know, it's like we know what your intention is, and we want to go and work with your intention. So yeah, code should just run unconditionally. So let's go and actually dig down into code a bit, okay? So this little piece of Java code is kind of like symptomatic of a lot of things that can go wrong in you know, traditional software development. We have this thing, it's a particular method that's going to go and actually go and get a barcode and use it to hunt for an item through some collection, okay? And what do? We return null, okay? Is null a good idea? Yeah, I mean, we're really over it now. We kind of feel that null is really a bad idea. You know, Tony Hoare basically mentioned years ago that it was his billion-dollar mistake, that introducing this into languages early on. But we kind of know what we can do these days. We can start using like option monads and all these other things. Some languages don't even have null at all, right? But yes, this is kind of like symptomatic of things that can go wrong inside of a programming environment. You're trying to go and get something, and you try to get it, and you just can't get it. So what do you do in situations like this? Okay? Well, one thing you can do is you can throw exceptions, right? Yay, exceptions. Good idea, bad idea? Yeah, you know, and we, again, in the industry, are kind of moving away from this particular thing. If you look at, you know, like Go's error handling, for instance, you know, it's kind of like we have panics, but we don't have exceptions, right? We have this thing where we're going to kind of like, you know, you return things back, and then you have to inspect the return values to see what happened and do something about it. And forcing that work onto the programmer in order to go and say, look, we're not going to let you hide things. And that can be a problem with exceptions sometimes. Bertrand Meyer, years ago, gave his advice about when to use exceptions in programming. And he basically said that you should use exceptions when you can't know in advance whether a call will succeed or fail. And that's an interesting thing to think about. When does that ever happen in programming? When you can't know in advance whether a call is going to succeed or fail. Sorry? Yeah, when you set parameters that you don't have much control over, yeah, there's things like that. I think the thing that's interesting is that it seems like when you really try to root out most of the problems that can occur, in many cases you can tell in advance whether something's going to succeed or fail. It's usually when you're at the edge of the system, when you're going and dealing with I/O, right? When you're going and talking to a disk, or you're talking to some third-party system you have no real control over, which is kind of like the case you just mentioned. So it's kind of like this interesting thing of going considering that most of the things that will lead to this scenario where we can't tell in advance whether something is going to succeed or fail is in areas of the system that we don't really have much control over. So it kind of leads us to this idea that, well, you know, in areas of the system that we do have control over, what can we do? So that we basically don't have to scatter it with error handling code. Okay? So it's funny to go and think about null as a particular case of a more general thing. You ever pass null as an argument to methods at all? If you do you tell people about it? Because it's kind of like an embarrassing thing to do, right? What is the bad thing about null? It's an interesting thing to kind of dig into. The bad thing about null. I think the main thing about null that's kind of interesting is that essentially what you're doing is you're forcing work on the receiver, okay? If you pass a null to somebody, the first thing they need to do is basically when they get that thing, they have to go and say, oh, this thing could be null. I damn well better check to see if it is null or not. And if you don't, then essentially you've got this little time bomb that's kind of floating around your system, right? But it's interesting to notice that that's what's going on, is you're forcing work on somebody else, okay? And in general, if you think about that in general, isn't that like a bad thing to do, right? If we aren't forcing work on somebody else in the system, we have less opportunity for error. So let's go and kind of carry this home a little bit. I saw this pattern years ago and didn't really have a good name for it. I think right now I'm going to call it like private language. So you ever have this sort of thing where you have like a giant method, and then what you do is you do all these things where you're gathering up pieces of information and you're setting Boolean flags, and then at the very end of the method, you basically have all these conjunctions and disjunctions of the Boolean flags, and you're saying, well, if this is true and this is true and that's not true and this is true, then I'm going to do this. You ever see that kind of thing happen at all? Yeah, it's kind of funny. Can you see that that's kind of the same as the null thing in a way? It's kind of like we're going and doing something, and we're forcing somebody to go and interpret it later, and it's something which is not easily interpretable, or it's basically prone to error when you're going and doing these sorts of things. So it's the distance between making a decision and actually doing something, okay, which is kind of problematic in many systems. So I kind of call this tunneling, okay? And tunneling is this thing where you basically are going and doing a bunch of things that force you to go and actually interpret things later. And you know, this isn't universally bad, right? Because you know, when you think about what happens quite often today in like functional programming, we're using like sum types or algebraic data types. It's like what you are is you're kind of like constructing this language of data that's a result of something, and then you basically have to go and sort of match it and work with it later on in your system, and that's okay, right? But the cool thing is setting things up in such a way that you're reducing the scope of input to something smaller that's easier to interpret and not pushing work onto the receiver in a bad way. So interpretation, you know, of very unstructured things is often a problem in programming. If you've ever heard of this guy, Alan Perlis, but he wrote this collection of epigrams years ago, just little sayings about programming. And he had a real way with words. Read this one for a second. So what's he getting at with this, right? Have you ever had that thing where you start to go and format strings someplace in the application only to go and actually parse them later in the application? And it's nice that we have, you know, reasonably well-behaved formats like JSON now and all these other things. But essentially, when you do that, you're basically introducing some barrier in your program which can basically lead to error, right? and you're doing additional work that you wouldn't have to do otherwise. So it's nice to kind of question these particular things, okay? But this is that general thing of like setting up things and having to interpret them later and having them be in such a format that there's a problem that can occur and it can kind of sneak into your program as errors. So can we eliminate these tunnels in programming? I'm going to basically say something a little bit controversial given the zeitgeist, or show you this. But so look at this code here for going and getting an item for a barcode. What's going on with this? We're essentially going and trying to go and get an item that matches a barcode, but if we don't, what we do is return back an item that represents the absence of an item. You ever see this pattern before? Yeah, so historically it's called the null object pattern. But this is kind of like a way of going and sort of saying, something bad has happened, okay, and we're going to go and sort of say, look, we can patch things up in such a way that everything's going to be okay, right? And you know, this is part of like a broader category of things. You know, it's like not a number, no object. Quite often empty lists or empty arrays will represent the absence of things. You can create objects that represent particular special cases in your code to go and deal with things like that. Is it a good idea or a bad idea? Yeah, you know, it's kind of funny. I was listening to, you know, talk yesterday, excuse me, Joe Armstrong's talk, and he's saying basically just fail fast whenever you can. And I think 90% of the time that's actually okay, but there's sometimes when you may not want to. And using a pattern like this is okay. But the thing about this that you have to kind of recognize is that when you are using something like the null object pattern, you can get into a situation where the thing that you basically go and return back is something which is taken to be real. If it's taken to be real, it can go and lead to other possible errors. So let's say for a system where you're going and gathering items and you want to go and sum up all the items. You know, if this item happens to have like a price of 0, that's fine. If we try to count the items and basically use that logic in making some kind of decision within our application, the fact that some of these items are null items could be something which goes and ends up kind of hurting us. But this thing of going and trying to decide, or basically deciding to do nothing, can be kind of handy for us sometimes. It allows us to kind of funnel things. It allows us to go and actually have like a wide range of input. We have output that comes back to us, and we basically don't have extraneous errors polluting our system as we go through with things. I want to show you another way of going approaching this. As we are working with, like, say, a sale class or something like that, which is going and getting items from some collection, you know, the code I showed you a little bit earlier. There's a couple of different things that can go wrong. One thing that can happen, as I showed, is that you may search for an item and discover that it's not there. And then we talked about, okay, well, we can throw an exception, we can return null. You know, we can essentially do what I just said, like have like a null item and pass it back. But the thing that's kind of cool that we can do is we can actually extend our domain and consider the errors part of our domain, okay? So with this, we have some listener that's going to go and you know, receive information about things that are happening in a sale as we're going and totaling things up and doing things. And we can just add another method, item not found, and pass the barcode, right? So see what's going on here? We're essentially saying this is an error, and rather than going and throwing an exception, rather than going and doing something kind of spooky with null objects, what we're going to do is we're actually just going to go ahead and say that error is part of our domain. And when it's part of our domain, then it's something that we can kind of deal with, and it's kind of hard to avoid. We can see that this is a particular thing that can happen in the application. It's interesting to see that, you know, this thing right here, we're kind of going and telling some other object about something which happened in our system, which is fine. You can practice the same thing if you're working in a language which has like sum types, for instance. And just go ahead and say, look, you know, here are the cases that are good. We also add in a couple of cases that are bad, right? So we have item added as one thing that could happen. We have sale total, but we can also have item not found as a particular thing that, that could happen in our system. But going back to this thing of going and telling through an interface about something that happened, I find it kind of interesting that it seems like a lot of error handling gets better when you start going and adopting this thing of like I'm telling an object to do something as opposed to going and saying, give me some stuff, right? Think about the typical thing. I'm going and saying, oh, get an item from some collection or get an item from some data store. And it's like it could return null, right? And that can be problematic for us. What if something is doing the work of going and getting an item or whatever, and then once it has it, it goes and says, okay, well, now that I have this, I can notify other people that are connected to me about the particular item that I have, right? When you're in a situation like that, essentially there's one less error. You can basically have, well, the error's actually been shifted to the place where you're going and getting things, but everything else is isolated from the fact that that kind of an error has occurred. So just to go and show you this in code, typical thing is to go to some data store, you know, get a person based upon an ID, for instance, check to see whether it's null or not, and if it's not equal to null, do some work, and we have a null check, and we know how problematic nulls are. We just talked about that. But the alternative is to actually adopt a tell style, where you can go and do something like this. You say to my data source, I have a particular method called withPerson. I'm going to pass in an ID. If that ID matches a person, that person gets passed to the Lambda, and the Lambda goes and does the work, right? So we're basically telling the Lambda to do some work based upon the fact that we actually, based upon the success of going and having done something like this, having gone and tried to retrieve things. Is there a null check here? Probably inside of withPerson, but the thing is we've isolated the rest of the code from this particular thing, which is kind of fascinating. This whole thing of going and telling rather than asking is very, very interesting right now culturally within programming because we are moving to functional programming quite a bit. But it's interesting to notice that telling just makes a lot of things easier in systems with regard to error handling. And in fact, if you look at Erlang, for instance, essentially processes in Erlang, they have like this functional core. They basically are doing all functional stuff inside, but what they do is they send messages to each other, which is like this tell style, which is very much like traditional object orientation. So organizing your systems in a way where basically you tell people about the data that you have as opposed to going and trying to get it from people can go and eliminate a lot of error handling that you would have otherwise. So asking for data can fail. Giving it when you have it cannot. So this thing I kind of see as basically something I call extending the domain, right? This thing that I was showing with like the sail listener, going and adding the errors into the interface and stuff like that. The word domain is rather rich in linguistics. Domain means something in mathematics, right? It's like you have the domain of a function, the range of a function, stuff along those lines. It's really the input of something, okay? The input of your cogitation or your computation. Let's take a look at another little example here. Suppose I have this array, and this array has like, ones and zeros. I'm going to say that the shaded boxes are ones, and the ones that aren't shaded are zeros. And what we want to do is we want to count the spans of ones. So if we look at this, basically there's 3 spans of ones here, the first one and the one in the middle and the one at the end. How do we write code to do something like this? Well, we can get our Ruby interpreter and go and write code like this, right, and cover all the edge cases. Okay, if the array size is equal to 0, the count is definitely equal to 0. Okay, if the array, let's see, first element is greater than 0, meaning it's 1, the count goes up to 1. And essentially what's going on with this is we're going and we're scanning through the array and we're looking at the current element and the next element. Whenever we transition from a 0 to a 1, we bump up the count. And then we can go ahead and just return that, and that becomes the count. The thing is that the very first thing is a special case. If we already are in a span, we have to go and put a 1 onto our counter. Do you like this code? Yeah, to me this is edgy code. It has too many edges in it, right? It has all this conditionality which is prone to error. What about this? Let's play a trick. Okay, so here I have my array again. I'm going to put an element on the very front of it. Okay, and this element is going to be a 0. And then I can do something like this. Okay, and it's like if you're not too familiar with Ruby syntax, just to go and explain this, ARY is our array, and I'm prepending a 0 onto it. And then once I've done that, I can use this function called each cons. And when you pass 2 to each cons, what it does is gives you each successive pair within the array. So you have the values at indexes 0, 1, 1, 2, 2, 3, and just all those things taken as a sequence. Then what you do is you perform a count. You're destructuring, so you have like the current and the next element. Every time you have a transition, you bump up the count. Is this code easier to read and deal with? Yeah, way easier. How many edges does it have? Not very much, right? But here's the trick. We eliminated an edge by extending the domain, right? And I hope you can kind of like see this thing that's kind of like, here's the domain, the input, and we're extending it by going and adding prepending an element. And it's very much like extending the domain when we're doing things like our sail listener, going and adding error functions to it. We're basically increasing the range of things, the things that we basically can consider as input in the system that we're going and working with. So let's look at another little example. Anybody here ever play guitar at all? Stringed instrument? Anybody know what this is then? Yeah, this is tablature, right? And essentially what goes on with this, it's a way of notating music for people using stringed instruments, and it's often easier to read than traditional music notation. Every line here is a string, and every number is a fret position, a position that you will place your finger on in order to go and play a tune. So years ago, I had this friend who basically was a musician. He says, I'd love to go and have a program that goes and outputs this for me based upon input that I can give you in a file. And what's going to happen here is that essentially, the first number in every pair is going to be the string number, and the second number is going to be the fret position. And so if you have this, can you just output Tablature for me? So I wrote a little program to do this. And it's kind of interesting because you can think of many different ways to do this. I tried to adopt a very functional approach to it and ended up with something kind of interesting. The key insight with this was recognizing that for every one of these rows, what I had to do is I had to go and produce a column, okay, like this. So that's basically the first string has a 0 on it, but I need to go and generate a column that goes and has pieces of all 6 strings. Then I take all those columns and I kind of like transpose them so I can go and print them out row by row, which is kind of odd. But before looking at code that does this, let's go and look at the possible errors that can occur with this, right? Just listing out the different things that can go wrong with this. Maybe we don't have a valid file name as a command line argument, where we can't open the file. File is empty. Maybe the file contains empty lines. Maybe a line has, not exactly 2, numbers on it. Maybe the numbers are malformed. Maybe there's like, alphabetical, characters there and stuff like that. So all these different things are possible. Writing code that goes and actually just tries to go and do a clean version of this. One of the things I kind of ended up with was this. You check to see whether a file exists. The thing that's coming on is the command line argument. And if it's there and you can open it, then you start doing this work, which is going through each line of it, splitting the lines, calling this function called tab column to go and build up the columns and transposing it and putting it out. You don't have to follow this completely. The thing I want to point out, though, is this. We're checking to see whether the file pass as an argument is valid or not. Do we need to do this? Is there a way of doing things so we wouldn't have to do this? And this is kind of like an area where you can kind of like stretch a little bit. Turns out in Ruby there's this, this environment variable called argv. Okay, not really an environment variable, but a global variable. And, argf. And what argf does is it basically goes and takes all the things that are on the command line, assumes that they're file names, concatenates them into one big swath of text, and then gives you that text as a string. So I'm kind of like in this thing where, okay, well, we'll just accept things, and if there's a problem, I'm going to get some kind of interpreter failure, that kind of thing. But I don't have to go and do the explicit checking. I don't particularly care about that. But this also goes and makes the program a little bit more general in the sense that I can go and put multiple files to go and actually have them all be part of one composition I concatenate together and have that work. So there's this fun thing you can do with errors sometimes, which is generalizing your problem a bit so that the things that can occur tend to be okay, right? And that's kind of part of this. Let's look a little bit further with things here. So that solves some of these problems. What about this? What are the cases where you have like less than 2 numbers on a line? We should probably go and flag that as an error, shouldn't we? We could. Could we interpret a single number in a line as something? Can we basically have a different interpretation? Sorry? Arrest? Could, yeah. That's right. We could interpret it that way, or we could interpret it as a 0. We have a couple of different possible interpretations. And it's interesting to kind of like play this game a bit and go and say, look, here's something we would flag as an error, but can we actually kind of like pun, the input in such a way that that does mean something? And this is, again, part of that domain extension thing. It's kind of like what we're doing is we're kind of going and saying, we're going to extend the range of possible inputs. We're going to sort of find that certain things aren't necessarily errors and give them an interpretation which is valid in the context of the system. Can this go wrong? Yeah, it can go wrong. And you have to basically determine what the stakes are when you're going and doing this thing in a particular language. But there's examples where this could be used all around us, like the square root function in most programming languages. What happens when you pass a negative number into it? Bad things, right? Yeah, we don't want bad things to happen. Could we fix, square roots so that passing a negative number is okay? You'd have to return complex numbers, right? And just, when you have the square root of -1, then you get a complex result, because in mathematics, there really is a definition of the square root of a negative number, but it's kind of like moving to another number system. But that's actually like more work than is necessary or anybody would really want to go and take on in most programming languages, so we just simply don't do that. But there's other places where we do this, right? So I don't know which language was the first to actually do this thing of going and taking negative indices on arrays and interpreting them as being like, start iterating from the very back of the list. But now it's pretty common, isn't it? for arrays and strings and stuff like that? What are the chances of going and having like an error when you do something like this? Can happen. But the important thing to go and recognize is that when you have something like this, what you're doing is you're going and making this bet that as you extend the domain, people are going to understand that you've extended the domain. They're going to understand what a negative index is. It has to become like a cultural or a documented thing within the system that this is actually the thing that happens with this. And then when people are thinking those terms, it's fine. It's one less possible error case and also goes and gives you a bit more flexibility in the work that you're doing. User interface. You know, it's kind of an interesting thing about this. I'm using domain in such a general way here, but it's like, say you have like a parking app. I remember using a very early parking app, and the thing that was kind of cruddy about it is that when I put in to park in a particular location, it would force me to go and have that time run out before I could park in a different location. So there's no such thing as having a 15-minute meeting and moving to a lot down the street, because it figured that once you'd parked there for an hour, you were there for the hour. Is that kind of ridiculous? Yeah, it didn't last too long that way. But essentially, you know, this thing of going in and saying, look, you know, our domain is basically, you know, the space of all parking spots, right? And you should be able to sort of like have your intention and do this and just have it work, right? It's like that's a valid choice that people could make rather than going and telling people that's an error. So yeah, extend the domain when the extension can be considered the new domain. That's pretty much a way of looking at this. Going back to our code here, all these different errors that are possible. You know, this is kind of like going in and carrying things a bit further. There's like a check function here that goes and checks for possible errors, reports if there's problems. You'll see that over here I say that we go to RGAF, we basically go ahead and we do this work to go and cut out all the lines that have nothing on them. We split so that we have an array of pairs. Then we do some more checks, and then we actually go and do the work that we have down here to go and actually produce the representation. It almost seems like our program's been segmented into two parts, doesn't it? Right? We have a part where we're doing all this checking. After this checking, we have a representation that basically just should work no matter what. And you'll see that the error handling just doesn't happen past that last check that we have there. And this is a nice thing to basically have in systems. Just go and get to the point where you do all this kind of checking up front, and then past a certain point, things are going to run to completion. And you know they are because essentially you're not dealing with, you know, you're not dealing with anything external. You've been able to check all these particular conditions, right? You could have something crazy like a divide by zero, you know, or a seg fault or something crazy like that. But for the most part, you just kind of know that once you get to a certain point, there's not much checking you have to do yourself. And this allows you to kind of like separate, you know, parts of your system into, you know, kind of like a soft center and a protective shell, right? Once we know what all these constraints are around us and we basically verify that things have satisfied those constraints, then we have this area where we don't really have to do error checking. And that's a really nice place to go and be within your code. So carrying this even further, we can use something which is kind of like a, you know, almost like an option monad approach. There's something called either in Haskell, and I kind of mimic that here within Ruby. Essentially with this code, we're able to go and just put everything in a line and do the work. Whenever there's a check that occurs, if the check fails, it passes along an error. And every successive piece goes and checks to see whether it's receiving an error, in which case it does nothing, it just passes the error along. Or it goes and sees that it's receiving the result of computation from the previous step. So at the very end, you get a string which either contains an accumulated error message or it contains the actual output. Okay, and this is kind of where a lot of people are going with functional programming, right? To go and sort of like say, look, we're going to use option monads and all these other things in such a way that we can avoid exceptions, and that's nice. But isn't this kind of like, yeah, I don't know. I have mixed feelings about doing this sort of thing, as opposed to going and checking in advance and just aborting computation early before you get to the main line that's going to go and run. Funny about this, when you start thinking about errors, you start thinking about things that can go wrong in systems, a thing that I keep coming back to is exceptions, as I mentioned a little bit earlier, right? We talked about exceptions briefly. I've always felt kind of weird about exceptions, you know, and I think a lot of people do, and that's why we're kind of like moving away from them in the industry a bit. The thing that kind of bothers me is that in a system where you have any kind of possible side effects or you're modifying state, all these other things, when you have your try clause and you do some work, it's like if you throw an exception at any point inside there, you have to kind of sort of make sure that the world is set up in a state that you know about, right, once you've actually gone and failed, right? Ideally, what we'd really like to have in many systems is almost have exceptions be like a time machine. It's kind of like, well, I decide to try something, and whoops, that didn't work, so I'm right here, and I get to go and find out that, hey, that didn't work, but I know that the state of the world is exactly the same as it was, prior to going and executing the try. Do we have that guarantee at all? We actually have to kind of work for it, and that's why I kind of feel the exceptions are almost like half of a language mechanism, in a way, half of an error handling mechanism. When you think about it, what this is really about, it's almost about like transactionality in a way, right? It kind of feels like transactions. And I don't like using the word transaction because it's so overloaded in the industry, but I think an interesting frame for all this is to go and say, what are our intentions? And once we know what the intentions are, the intention can either succeed or fail. And then we can go and sort of think about, what's possible in that frame within these things. So to give an example, practically everybody's music player in the world has some kind of a shuffle mode on it, right? You're able to go and shuffle, your playlist and sort of have things in different orders and stuff along those lines. And this is really actually a rather deep domain. Most domains are. There's a lot of really cool algorithms you can use to go and shuffle efficiently lists of things. But it's interesting to think about naive code to do this, right? We have, a list of things. And one easy thing we could do is just go ahead and say, let's go and call the random number generator, get a random number, and take that random number and kind of mod it in order to go and actually determine the next track to play. The only thing about that, though, is like, what if, your random number generator gets stuck? Keeps returning the same number over and over again. You're going to have people like hearing the same track, and maybe it's not even one they even like, over and over and over again. And we know that a decent random number generator is not going to go and give you, a large swath of the same thing over and over again. But we try to kind of like piece together, that constraint in our code a bit. And we say, okay, let's go and have a while loop, and essentially, we're going to call a random number generator, and essentially every time it's equal to the last one, we just sort of like, try again, right? Which is a really naive way to do it. Is this code okay? It's like, it's really kind of interesting as developers. You should always be thinking, it's like, what's the worst case for this? And it's like, oh, my loop could get stuck. It's kind of ridiculous, right? And of course, processes are fast enough that you would never think that this would get stuck forever, right? It just really wouldn't be a thing that's likely to happen. But still looks kind of, like ugly code in a way. What else could we do? Well, we can essentially go ahead and sort of like just, get the current one, and if it actually happens to be equal to the last one, just go ahead and get the next track, next track in the list, and mod by, the size of the list, and go and use that one, right? Our code's gotten more complicated, hasn't it? Right? It's kind of like, we've done this particular thing, and it's like we're worried about going and showing, playing the same track, over and over again. But it's an interesting thing. What if you went back to the people who are commissioning this work from you and said, I can solve this problem in a pretty easy way, but it's going to have this interesting side effect. You're never going to play the same track twice at all, right? And the solution you're thinking of is to go and say, okay, here's my list. I shuffle it. Then basically what I do is I have a copy of it. And I just basically, after it's been shuffled, I go and play a track and just take it off the list. And then at a certain point, you're going to end up not having anything in the list. And then you basically do that again, right? Is our code much simpler when we do something like this? Yeah, it can be, right? But notice the thing the thing to me that's really interesting about this is the way that we interact with requirements, right? We were actually going and saying, well, look, we can basically make our code less complex if we change the problem a little bit. And it's great when you're in an organization or in a context where you can have that kind of play to actually say, look, this is not really, here's, something you might think is like a hard and fast requirement, but if we change it a little bit this way, it makes our code easier to deal with. And it feels like we should feel comfortable doing that sort of thing. Going in, like looking at generalizing our code in particular ways that allow us to go and basically avoid edge cases and make things a bit easier to deal with. So it's kind of funny. Anybody hear of like the 5 whys at all? It's kind of like, asking, if there's a fault and you're doing like root cause analysis, why did this happen, and then why, that kind of thing. It's interesting because we can play the same game when we're designing. We can have this thing of like, well, I'm opening a file, okay? And when I open the file, something can go wrong, okay? Oh, so I have to handle errors, right? That's just the natural thing that we have to do with this. But the important thing to go is say, okay, well, why am I opening a file? Oh, I'm opening a file because I need to read a config, right? I need to read this configuration, populated configuration database. And then you say, well, gee, why do I have to read a configuration? Well, it's because I'm trying to initialize the system so I can go and bring it up, right? At every step of this chain, you can start thinking about alternatives that can basically be things you can explore if one of these things goes wrong. And as I mentioned earlier, it's like this, there's an interesting thing where, a lot of error handling is basically related to the distance between detecting a problem and actually deciding what to go and do about it, right? When you follow this chain, you might start thinking about alternative courses of action that you might want to go and explore. Like, for instance, you might go and say, well, gee, if I can't read the configuration, is it okay for me to go and actually create a default configuration and then notify people and let them know that it's like, okay, well, we brought the system up using the default configuration because the other one, and it depends upon the context. In some contexts, that's okay. In others, it's kind of like that to be a disaster, and you really want to go and put people through that sort of thing. So we should always question errors. I don't think we're going to be able to eliminate errors completely across systems, but to be able to go and say, it's like, well, why is there an error here? Could the system be organized in different ways where we didn't have that error? Could we alter the requirements in such a way where we wouldn't have to go and do that particular thing? And this, going through that particular thing, we not only get the benefit of having, fewer potential errors, but also simplifying our systems sometimes. Okay. So let's talk about edges a bit more. It's interesting that back in the early cable days, like everybody had like a set-top box, and you'd like, you have your remote and the software's firmware in a box someplace. And nowadays, it's like everybody can use an app on their phone to go and change things depending upon what streaming service they use, and just connect with the TV, like wirelessly, and just do that sort of thing. It's interesting with this to go and notice that, we're putting the network between things, and we've been doing this for ages in the industry, putting the network between different things. And it's kind of nice. The cool thing about this, though, is that when we do this, we quite often basically allow ourselves to go and have a different kind of system than we would have otherwise. I draw a distinction when you're doing design and systems between what I call tended systems and untended systems. And the tendency is meant to have way more tended systems these days. So what do I mean by an untended system? It's like, imagine you have some probe you've sent off to the far end of the solar system, and it's like there's a lot of things that have to really always work there because there's not going to be anybody over there to fix that problem if the problem occurs, right? So you can't count on having somebody there to go and actually deal with those particular issues. And there's lots of real-life systems where you have that kind of, you have to be really careful about errors because, essentially, there's just, there's no alternative. There's not going to be anybody to go and fix things. But as we put more and more things on the network, quite often you're working in organizations where you have operations support and all these other people can help out when something bad goes on. It can really allow yourself to get more into this fail-fast mode with things. But it's not universal, okay? Fail-fast is a nice strategy, but there are many cases where you just, you have to keep a system running no matter what. And it's like, like Erlang is really good for things like this, like telephone switches and stuff along those lines. So thinking about that design space between tended and untended is rather valuable. Elevator controllers, right? It's like, you don't want to be in a situation where if the network goes down, people are stuck, right? So you have to have stuff that runs no matter what. And this fundamentally alters the way you design systems. And not every system is like this. If the typical thing in Unix is to fail fast, they're stringing together command line utilities on a command line. It's like, that's great because you have an operator. Everybody knows that you're failing fast, and you have to tend things, and at least have somebody who's going to look at the logs and see what's going on with things. So it seems like for robustness, you need a human in the loop that can basically solve problems when they occur. The interesting thing about this, and we kind of skip ahead, is that when you're working in a system, if you're using a language like Erlang, what I find kind of fascinating is that all the stuff that you have in Erlang with things like supervisor trees and all these other things, essentially that's a way of mimicking the human you would have in the loop normally, right? It's kind of like, you can say, let's go ahead and exit, let's fail fast, and that's fine. And this is like saying, okay, well, if this thing fails, we're going to put some process inside to go and heal the system, to actually go and say, well, I need to go and reboot this thing. And that's not us saying that. It's the particular supervisor process that we have within Erlang to do these things. So this really is, I'm going to kind of differ a bit with, a lot of people are looking at systems like this and, like Erlang and Akka and stuff like that and saying this is the way to go for everything. I think it's really a cost choice. It's a safety choice. You have to decide whether you really are in one of those systems where you have to have that kind of recovery built into things or not. There's all different kinds of systems, and the way we approach error handling really does depend upon this thing of whether it's a tended or an untended system. So yeah, safety is pretty hard work. Where do we want it? There are places like, operating system kernels. Would you want to be the person that calls Linus up in the middle of the night and says, hey, my kernel's not working? It's kind of like, so there are certain things that you want to go and have a degree of, care in coding. You might want to use proofs, very strong types and stuff like that to make sure that these things will just sort of like, be robust in the face of these things, and other places where you don't. So yeah, error proofing is important when there is no real supervision. Another aspect of all of this is really is there a cost to going and making our code safer and safer? I notice more and more people are, people are doing a lot with like Rust now and basically trying to go and eliminate lots of possible error sources by being very strict in the language. And anybody use Rust at all? Yeah, so it's very nice. The thing I think is kind of interesting is to go and notice that there's like an outer feedback loop that's not really part of the language, it's also part of the teams that are producing things. That's kind of interesting. There's an interesting experiment that was run about 10 years or so ago, I think in Germany and in England. And it was to go and remove all the traffic signals in urban areas, in inner city areas, and small villages and stuff like that. So what do you think happened? Well, there's a little blurb there telling you what happened. Actually, accidents were reduced when you removed the signals, and you also removed like the guidelines to go and show where you are in your lane. Why would that make things safer? You become more careful because you're like, oh, am I in the street or am I like on the sidewalk? I don't even know. Better slow down, that kind of thing, right? Isn't this counterintuitive though? Yeah, it's kind of an odd thing. And it's like, you know, I think that we've got this really interesting cultural thing going on in programming right now with regard to errors, because like the Rust community and several others are dealing with this thing of like, let's make sure that these things can't happen and da-da-da-da-da. Then you have people like an airline going and saying, well, errors are going to happen. Let's go ahead and sort of like build a supervision process to make sure that, you know, we can at least recover and we can do good things if something does go wrong. Two very fundamentally different philosophies. The other dimension I'm kind of like bringing to this here is the degree to which being careful or actually care is like engendered in programming by having an element of hazard. And the personal story that I'll tell about this was when I was in university, which is ages ago, got my gray, right? I was learning Pascal, which is like a very early language by Nicholas Wirt. And it was, you know, first programming language. But I'd already learned how to program before my first programming course. I learned how to program in C. And it was fascinating because I was at the computer lab one time and sitting next to this person and looking over, and this is like almost the end of the course, and realizing that they were getting array subscript out of bounds exceptions, and I'd never seen one before in my life. And I thought, wow, you know, she's getting this on her screen. It's like, how come I haven't seen that? And it's like, oh, when you work in C, you learn very quickly not to do this, right? Because once you go out of bounds, you're in this terrible debugging hellhole, you know, and it's kind of rough that way. So yeah, there's this thing where basically the possibility of error goes and gives us a bit more diligence in certain spaces. And I think that's something we have to kind of like factor into, you know, our broad view of what errors are and stuff like that in systems. Yeah, so I don't even really like the word error anymore. I think it's kind of an interesting thing to try to reframe. You know, there are things that can happen in code. We should try to go and challenge them and see if we can get rid of them. You know, things like I mentioned earlier about going and actually making them part of the domain, like item not found is a thing that happens in your code. It's not something you have to go and create an exception for specifically. All those things are worth going and dealing with. And then also go and ask yourself, can I have a system where, you know, that error is impossible? And just asking that question sometimes it allows us to go and get to a place where things can be much better. So I think the thing I'm kind of, you know, trying to explore with this is that, you know, code can work under many conditions. And there are conditions that we don't want our code to work under, and we call those error conditions. So the big question is, can we actually go ahead and increase the number of conditions our code can work under, often by generalizing or like a bit more design, and get to the point where it just kind of just runs unconditionally. It doesn't tell the user, hey, you can't do this. It basically sort of like curtails some options so they don't even think of doing the bad thing, right? That's a user interface type of thing. Using structure inside of your code that basically is less prone to error, okay, or the good thing becomes much more natural to do. And I think, you know, it's worthwhile. You know, error handling is not just option monads and exceptions. Those are mechanisms. You know, all this stuff is design, and we have to kind of like deal with those things that way. So I want to leave it there, open for questions. Thanks.